Good morning, everyone. I'm glad to have you here this morning. To introduce myself, I'm Carla. I'm the marketing manager here at FuseForward, and I'd like to welcome you to the final remote control webinar for the year, as well as the 9th in the series. So today's episode is Building Smart Infrastructure, and we're going to be taking a look at the Ryerson Smart Campus that we've been working on with Ryerson University. Joining us today, we have Mark Dam, our CTO, who's heavily involved in this project. And we also have, and we'd like to welcome, Jen MacArthur, who is a smart building expert and associate professor at Ryerson University. All right, well, it looks like there's a lot of people here already. I'm not going to take any more of your time. I'm going to hand it over to Mark.
How's everybody doing today? So this is, as I said, we've got a different occasion today. Instead of listening to me and sharing my insights on a whole bunch of things, we've actually brought on our guest speaker today. Guest speaker is Jen MacArthur from Ryerson University, currently over in Scotland. So we've got an international collaboration going on in people all corners of the globe, which is all good to see. What we're going to talk about and share with you today is some of the steps that we've already taken. We're about a year into our current project with the smart building inside Ryerson. I'm going to talk through that a little bit, but before we jump onto that, let's got a little poll that we want to ask folks. First question is, what are you most interested in learning about during today's webinar? If you want to go and jump that in, are you interested in campus operations improvements, smart building trends, data analytics strategies, IoT device and sensor management, the academic and research approach, or other? Please share. More than happy to go through. We'd like to understand what the market, what the current membership is today looking for, and make sure we can tailor a little bit to answer your questions. Edric, I'm sure you're out there going through and getting ready. Carla, you've got that ready?
Yeah, it's running. We have 63% of people voted. I'll give it a couple more minutes, or not minutes, sorry, seconds. We have smart building trends, 35%, or actually more than that coming in. Then data analytics strategies, IoT device and sensor management. So I think people are really, I'm getting the sense that they're interested in the trends of smart building.
Perfect. Well, let's go through and we'll tailor the discussion today, and that's perfect because that is definitely Jen's expertise is in that area. So let's go through. Let me share with you a little bit of a background first off on what we have today. So, what is Ryerson? Ryerson is a 50,000 plus university in downtown Toronto. So Toronto, being one of the largest cities in the world, is in the heart of Canada in Ontario. Everybody in Toronto that lives there thinks it's the center of the universe, which I grew up there, so sure, but I live in Vancouver now. It has 40 buildings. Now, the interesting thing about this campus is it's not a typical campus. It's not a campus that is all by itself. It's actually in the heart of downtown. That means that you can walk from one area, which is a shopping mall, and go to one of the campus buildings to go to class. It's all within that dense downtown core. It's also only got, but it does also have some residential space. So it's got 1,700 students that are actually living on campus in campus dormitories. So those 40 plus buildings are things from old legacy buildings to a learning center in downtown Toronto, which has all been wired for sound and has new SCADA systems and everything involved, and we can sensor and monitor everything going on. So that's one of the reasons. Now, the key thing around this, and I'm sure Jen can share with you, it's not just that we've partnered with Ryerson as the labs, but we've also partnered with the facilities organization at Ryerson. What does that mean? It means that we have the facilities operation, we get access to their building information systems, we're linking in their SCADA systems to ingest all the data, and we're looking at how to secure all of that as well so that we can start looking and predicting new future performance. So what are we trying to achieve in this project? So our goal, what are we trying to do is, we're looking at the campus in Ryerson as a means that can we optimize the campus operation using predictive analytics and new IoT devices. So what do we mean when we say IoT devices? Well, what about we're all in lockdown mode and we're looking at airflow monitors. Do you realize that we can probably start monitoring airflow to see virus in the air using HVAC systems? So those are new sensors. That's IoT. but we have to go and connect those in to a central monitoring system and be able to go through and monitor what's going on, to be able to react to it, to basically put people, teams, or know what's going on in that environment and react to all of that. So part of what we're trying to do is look at improving environmental performance, reduce traffic congestion. So even in the downtown core in Toronto, we're looking and say, can we look at mobility patterns of the students between all the different buildings? Can we figure out what they do, where they go to a lunch spot or coffee shops, and how they move, to understand the mobility patterns so we can better manage the flow patterns and decrease congestion in certain areas. And then, of course, along with that is energy cost. How do we go through and manage the energy footprint by doing things like dynamic set pointing on our HVAC systems and on our control systems? Now, what Jen's going to share with you is here's what we're doing right now within the Ryerson environment. What we're doing from FuseForward's perspective is we're very keen to be part of these research partnerships to do technology development. Now, where are we going? We started working on smart city projects, water, wastewater flow patterns about 10 years ago. And what we've been finding is we need to know more and more with new sensoring technologies, and we want to commercialize technologies for everybody that's managing smart buildings, smart cities, energy grids, and these new green energy projects, and all those other components that require technology systems to manage and monitor everything in an autonomous way. That's our driver. So it's very much a partnership between industry and academia to take new technologies to market. And on that note, I'm the industry guy. I'm going to share and let you go and hand over the keys right now to Jen. And Jen, I look forward to hearing what you have to say.
Great. Thank you so much, Mark. So while I am getting my presentation up, just a bit of background. Mark and I think we started working with FuseForward back in 2016, I think.
Yeah, it was a while ago.
So it's been a few years. I've actually been working with the Ryerson Facilities Management Group since 2014, when I actually started as an academic at Ryerson. And over the years, it's been really, really amazing to see some of the opportunities that we have. And one of the opportunities we have on any campus is that there's a lot of pre-existing data available. There's a lot of sensors and there's a lot of systems that we can tap into. And one of our big goals of this project is to figure out how to use that legacy data and supplement it with new sensors and new tools to really enhance how we're actually able to manage the campus. So the vision that's really driving a lot of the research that we're doing within the smart building group at Ryerson, the Ryerson Building Research Group, or Smart Building Research Group, is this idea of a world in the future where all of our infrastructure, our buildings, our networks all work together. And they're actually helping us to really tie everything. So we can see the buildings, we can see the communications, the cars are able to manage themselves while they're on the roads. The grid is able to respond to fluctuations. We're able to store renewable energy and make best use of it when we need to. We can manage everything that's going on. And this actually really helps us to manage this built environment and really find these optimizations. Within the smart built environment, there's a lot of different pieces. So we've got the communication network and the architecture and the secure environment that we need. We have the interaction of all of the different devices, whether it's motorized vehicles, pedestrians, cyclist vehicles, mass transit. We have all of the site infrastructure and the major infrastructure that's tying things together. Both, the physical roads that are supporting the transportation, but also our communications networks, our electricity networks, our water networks, our waste management systems. And then finally, we have all of the buildings that actually fit within this environment and wind up being some of the primary consumers of energy. If we look in Canada, buildings use about 40% of Canada's energy and generate about 1/3 of the greenhouse gases, and transportation is roughly equivalent. So between those two aspects, we really are having a lot of impact on both carbon and kind of energy security. Now we have 4 research labs in this project that we're working at with FuseForward, which is called the Smart Campus Integration Project. We have the Smart Buildings Lab that I lead. We have the Smart Mobility Lab led by Dr. Bilal Farouk, and they do a lot of work on disruptive transportation technologies. We have the Smart Infrastructure Group led by Dr. Song-In Lee, who's looking at how to optimize and manage and do event detection on very large infrastructure systems. It's like water supply systems, sanitary systems, waste management systems, and electricity. And then we have sensor fusion, which overlaps with all of our various labs, and the creation of digital twin. And Dr. Ahmed Shekhar is our fourth collaborator on this project. And his specialty is in hyperspectral cameras. So infrared and different ways of looking at buildings, both with visible and non-visible light. So you can actually detect issues that might be happening. You can do some thermal imaging. And actually mounting those on drones, on backpacks, and on vehicles so that we can very quickly create these scans, as well as LiDAR, which is a laser scanning technology that we often use to very rapidly generate digital twins. So the four co-PIs we're working together with FuseForward on a 5-year project to create a full digital campus really focused along one case center building. And that's going to be the highlight that I'm going to be showing you in a little bit. Now, the vision for the Ryerson Smart Campus, as Mark was saying earlier, is really to be able to reduce the congestion, to be able to make best use of the facilities, and to optimize the performance. And this is partly environmental, it's partly economic. We want to be able to predict issues before they happen. We want to be able to predict failures before they're catastrophic, when you can just be changing a gasket or doing a small piece of maintenance rather than having to replace a large and expensive piece of equipment. And we've done some work on some fault detection algorithms that are actually feeding into this project that will let us actually determine when a boiler is starting to scale, when we're going to start to see decreased energy use or decreased energy efficiency on these boilers, so that we can actually respond before we would ever have any way of being able to tell otherwise with its data analytics. The other thing here, if you look on the right-hand side, we get these new scenarios. And there's been a lot of work on using digital twins on doing emergency preparedness, disaster response simulations, and trying to get a sense. With our smart campus buildings, we have a whole virtual campus of the entire, or a whole virtual model of the entire campus. We could actually map in and tie into the hazardous material databases so that first responders would actually know going into a building which rooms have stockpiles of flammable, explosive, or noxious chemicals. You can see that with the masks we're living in the post-COVID or pan-COVID world, and this pandemic is affecting every part of our lives. One of the things that we're looking at with this case study is how can we actually help to manage a safe return to campus with the pandemic. And I've had some really great conversations with the Director of Facilities Management about how now that we know that the buildings are being used, we need to start cleaning them again, because we have certain people with permission to return to campus for essential work, such as critical research. But we don't actually know when people are there. So by using occupancy sensors, by using predictive algorithms, by actually using these supplemental IoT devices, we're going to be able to actually come up with demand-driven cleaning schedules. Rather than simply saying, I guess we have to assume it's always being cleaned, we'll know every time, say, 5 people have used the washroom facilities that they need to send somebody in to do a full sanitization. Right, so it helps us to really better respond to this. It also helps us to map potential contamination routes. It helps us supplement contact tracing, which is already a current application of IoT technologies to try and help do this contact tracing. So we're really looking, there's a really great opportunity for smart buildings, smart campuses to help to make these not just smart, but also healthy and a lot safer in this pandemic context. Now, when I first started at Ryerson, I was trying to wrap my head around what this kind of smart campus would need to do. And there's a quote on the screen, and this was just a piece of, just came from a conversation I had with Paul Martin, who was the facility engineer at Ryerson back when I started. And this is what he said: got 100,000 pieces of information across my desk every year. If you can tell me the 10 I need to pay attention to, you've got my attention. It's such an enormous volume of data that we're trying to navigate. So being able to develop a system that will actually sift through, find the aberrations, find the things that aren't working properly without having 150 nuisance alarms going off every hour, which for anybody working in the smart buildings or even just the regular building control sector will know is often par for the course, it's really important for us to be able to really zero in on what's important. So we do have one more challenge, and this is the fact that we're not dealing with new buildings. Ryerson is a relatively new school, but we're still in the downtown core. We're still occupying a lot of buildings that were built in the 40s, 50s, 60s, 70s, 80s, 90s. These are not brand new buildings designed to be smart building in the first place. In other jurisdictions, it's even worse. The picture on your screen here is Amsterdam. And you can see, this huge amounts of the city built in the 17 and 1800s. And they're trying to make it a smart city. But how do you do it? There's the very expensive way of going in and installing a smart building system in every single building and adding all of these brand new sensors. But there's a cheaper way, which is rather than trying to surmount that obstacle of creating the data, is actually tapping into the networks of data that already exist. And that's one of the big things we've been working on here. So our research objective overall, and the image on your screen now is the DAPHNE COCKWELL complex, which is kind of the core of our digital twin model that I'm going to be sharing with you, is how can we take data from a building not designed as a smart building. This is not a smart building per se. This is a building with a regular building automation system, like any building built in the last, say, 15 to 20 years. But it's got supplemental sensors, it's got supplemental meters. We have the ability to install other devices as we need to be able to complement what's already there. And we've been able to work to extract the data from these legacy systems and find a way of getting access to that data so that we can do our analytics and we can do these smart building applications of fault detection and diagnostics, which is FDD, doing real-time energy optimization, and also doing this actual informed maintenance and informed cleaning. One of the things about this energy optimization that I think is really important is that we design buildings to have a certain level of performance, and left to our own devices over time, that performance drifts. And typically you'll lose about 15 to 20% of your efficiencies of the buildings over about a 5-year period. And if you continue to do it, you'll keep losing that efficiency. So we'll sometimes do what's called recommissioning, where you go back and you bring everything back to your day one. So you wind up with a sawtooth. So you have periods where you're losing energy and you're wasting energy. You reset it, you have another period. We're trying to do two things. First off, we're trying to keep ourselves always at that top. So we never have the drop. We never have this decrease or this wasted energy. But second off, sometimes the design point isn't actually the ideal point. The use very rarely matches exactly what the design engineers intended, and it might be possible to find more efficiencies. So we're actually working to see if we can actually make the buildings more efficient than they were designed to be, not just as efficient as they were designed to be. So to do this, we need access to data. And here's an overview of the data streaming strategy. And just in layman's terms, we have this BAS. This is the building automation system. It's basically all of your room thermostats, all of your equipment controllers, and everything that basically operates any modern building. Then we have a monitor, and it was developed by a company called AFD Tech, working in collaboration with the building automation system vendor. And it's basically just listening. It's on the network, and it looks for change of value data on the building automation system. So we worked with the system provider and said, every time a sensor value changes by 0.1 degrees or 1% relative humidity, send a signal to the network. We will intercept it with this monitor. And then we're actually going to pick it up with the data streaming machine. That gets passed through a one-way connection across the secure firewall, because this, of course, is the campus system. We'll get into cybersecurity, but without this firewall, without this one-way connection, you could actually go through if you could actually hack through this, you would be exposing the entire building automation system to remote hacking. And this is something that's often a concern in smart infrastructure, is how do we manage this? A lot of water treatment plants simply don't allow their SCADA systems to be accessible by any internet device, which means you have to be physically on the plant sites to be able to access them. That's one way of dealing with cybersecurity. But this is the other way. We pass securely from one device to the next. Then we can pre-process the data on a server, and then we have a two-way virtual private network to FuseForward's cloud, where we actually keep our data in a database. So we've got a few challenges that we had to overcome to get here. First off, building automation systems will always advertise their BACnet, their Modbus, their open protocols. What they mean is that they're open at the edges. So you can actually find your, you can communicate here with anything using an open protocol. Any of these devices, any of these access points you can. But from here all the way down to your main network, this is all proprietary. So once you get inside the hub where you can actually see everything at once, it's no longer open, it's the controls vendor system. So these wind up being very, very closed systems. And the only way that you can actually access the full system is through the vendor GUI. Or if you're qualified with something called NC4 certification, then you can actually get in through the API to do what we've done with the monitor and actually extract that data. The second thing we need to do is we need to ensure network security. One of the greatest fears of smart buildings is that somebody's going to be able to come in, hack into a thermostat or a Wi-Fi node or a temperature sensor or a CCTV camera or something, and use that to get into the security system and hack through. Especially when we're dealing with wireless devices, especially when we're dealing with internet-enabled devices. One of the big challenges of IoT is this question of security. So this is why we've set up that one-way only system where the optimization can be done on the FuseForward side, from the cloud to the secondary data streaming device. But that's always done on a virtual private network or a VPN, and that way we never have to deal with any sort of exposure to the internet. Then we can query the data on the cloud into our visualization and into our digital twin, but we're never exposing the real data or the real systems in our visualizations to people. The third problem, of course, is how do we make sense of so much data, right? We don't just have 100,000 pieces of information coming across our desk. There's about 5 billion changes of value per year at the DAPHNE COCKWELL complex alone. That's billion with a B. So this is a lot of data that's coming in. It's heterogeneous data. So some of it is temperature sensors, some of it is on-off switches, some of it tells us what mode equipment's in, some of it is frequencies. There's all sorts of different types of data. So we need to sort it, we need to make sense of it. So we have two databases that speak to each other. We have a NoSQL database that basically just keeps the time and date, the unique point identifier, because we've assigned a unique point identifier to every single point in the entire facility, and the associated value. And then that can be connected behind the scenes to a MySQL database that we've created that actually allows us to look at the different relationships. So I just saw a quick question in the chat. BAS stands for Building Automation System. Sometimes they're also called Building Management Systems, but BAS or BMS, they're interchangeable. They basically mean an intelligent building system. So the MySQL database basically connects these different point IDs and tells us what equipment they're associated with. What type of data are they storing? What's the dimension of the data? And the equipment that maybe it's drawing from a particular piece of equipment. Well, is that equipment fed by another piece of equipment? Is it feeding another piece? Where does it fit into the hierarchy of the building? What about what room or rooms is it serving? So we can actually keep track of zones, we can keep track of locations. So we can say, well, tell me every piece of equipment that's associated with this room. Tell me every piece of equipment that is providing air to the first floor of this building, because I've had an issue with, there's been some sort of contamination. I need to make sure, I need to get a sense of that air path right away. Our data model lets us do this. And the data model isn't just confined to the buildings. We've used the same data structure with some obvious customizations across the different domains, so that we've got a full smart infrastructure model and smart transportation model that we're knitting together for the campus, so that we can basically deal with this data consistently across all of these different domains. Because the movement of people outside it becomes very important to us as when we're looking at the building, because those become our occupant flows. So, and that's all one consistent system. So we need to be able to look at transportation elements. We need to be able to look at smart grid and the different electricity and water flows across the campus and how they relate to what we're seeing in the building. So the DAPHNE COCKWELL complex, I'm going to give you a quick video and an overview of this digital twin. This was built 2 years ago. It was just opened about 1.5 years ago, first as labs and then the residential tower. I know there's some discussion behind the scenes of Ryerson only has 1,700 residence beds. Yeah, this was fairly new. So this was fairly, like, this actually doubled our residence capacity. We're surrounded by condos. We're surrounded by all sorts of apartment buildings, but Ryerson itself didn't own a lot of residential space for our students because it was really prioritizing the academic space. We now have the ability to build more, and there's new residential spaces in all of our new buildings. So the academic podium is the first 8 stories of the building. Then we have a mechanical penthouse, and then we have a 19-story residence towers. And we have over 10,000 building automation system points. So this is 10,000 discrete points that are picked up on sensors that are scattered all over the building. We have airflow monitoring stations, we have temperature sensors, we have occupancy sensors, we have all sorts of different aspects of it. And we have a lot of submeters as well, so we can really drill down into the energy consumption. Now, to turn it into an intelligent campus, we're trying to get all the different data sources into the interface. So we're pulling from our time series database, we're pulling from the MySQL database, we're pulling from some of the computer-aided facility management systems that our facilities management partners have actually provided for us. And this has allowed us to simulate it. And this is just a quick picture of the digital twin that we have actually created with Autodesk Revit. What I'm going to do now is I'm going to show you a couple of videos that were created by Dr. Karim El-Mokhtari, who's a senior research fellow in the Smart Buildings Research Group, that actually go through some of the functionality of this twin. So I'm just going to hand over to him.
Say now we want to compare temperature recordings from the last 2 weeks of January inside the room and outside in the corridor. We select these 4 assets, choose the start and end dates, the type of measurement, T for temperature, and we show the charts. The assets are highlighted with the same colors as in the charts. The box plots show that the median temperature inside is lower by almost 1.5 degrees C from the outside. But the variance in the corridor is higher as the box plots are taller. The line chart gives more details over time, and we can see a significant fall that happened on January 20th around 10 a.m. A cool feature in the viewer is that we can land on level 1 and walk inside the building. We can even change the focal length of the camera to capture more objects on the viewer. We can make the view more realistic by showing all objects. How about flying outside the building and getting some virtual fresh air? Unfortunately, the streets are empty and it's better to get back to level 1. Suppose I'm a technician in this corridor looking for an asset. On my tablet, I just type the code here, FCU16, and it is highlighted for me. The last thing I would like to show in this demo is that it is possible to use another color algorithm to enable comparing rooms visually using a heat map. As we are visualizing CO2 levels, the rooms with lower median CO2 levels are shown with a bright green color, while a darker green indicates a lower air quality due to higher CO2 levels. We can also define which type of aggregation function we want, and if you pick the max, these 2 rooms are in red as they went at least once beyond the predefined threshold of 800 ppm during this period of time.
So that was just a bit of a taste of the work that we've done on the digital twin. Now, those are just a couple of short snippets. Dr. Al-Makhtari has actually created a full-length video that's runs about 8 or 9 minutes, and that's going to be available on FuseForward's YouTube channel. So that was the big picture of these smart buildings and the digital twin that we've been doing. We're definitely very happy to answer questions as they come up. But right now, I think we'll be just handing back over to Mark.
Thank you very much. And I am going to share my screen again and move on. And you're not going to be able to see me right now, so you see my lovely picture right now, unless Carla can go through and start my video again. Anyways, what I wanted to share a little bit, and thank you very much, Jen, for that insightful information and summary of what we've accomplished in the current 12 months that the project has started. As you are probably well aware, we have been working since 2015, so there's a lot of background work that we've done on this as well, which included things like ontology modeling, taxonomy structures, and understanding the current state of the art in all of those different labs. And there's a whole bunch of research reports and academic papers that have been published out of this, which I'm sure if you're liking some information, we're happy to go through and share that. What I do want to share a little bit right now is a little bit about our Intelligent Systems Alliance. So just like Ryerson, we are not just working with Ryerson, we've actually been working with a number of other universities and labs and continuing to go through and lead the charge in building intelligent systems. What are we trying to do here? Well, what we're trying to do is do technology development spanning both academic and industry. So we've always seen where the academic world is building and doing all these great little projects to demonstrate stuff, but how do we go and get that into mass adoption? And that's where the industry partnerships come into play. So part of our alliance here is to basically create that bridge between what's coming out and going on in the labs and how do we start getting that out into the field where people and organizations can start to use it. The other focus of our alliance is all around advanced analytics and technology for critical service providers. So we've seen that we're working with buildings and a campus environment. But you know, some of the areas we see practical applications are things like what can we do within a healthcare setting? What can we do to make our office buildings safer as we start looking at virus and virus contaminants inside those environments? Can we start going through and looking at, as Jen said, looking at emergency service dispatching, situational analysis, so that if an emergency situation happens, we have much more streaming available in the way of data and able to go through and have systems to help us improve our decision-making around that. So part of our alliance, we've actually been doing this. FuseForward has been leading a number of projects since around 2007. And we have a track record of actually working with a number of organizations to do this. Some of the past organizations that we've worked with include York University, Mohawk College, Brock, University of British Columbia, University of Northern British Columbia, all funding students and labs to do different component projects that we've currently incorporated into a number of our technology platforms that we're now using to deliver services into the marketplace. Currently, we're working with Ryerson and Simon Fraser University. You've now heard the project from Ryerson. Simon Fraser, we're currently working on big data problems and how do we manage all of those big data sets? How do we use different technologies like Spark to go through and stream it, to do ingestion, to calculate indicators in real time? That's the kind of work going on inside Simon Fraser. Happy to go through and do another talk on that in the future. And we're currently working to put in a couple of projects with British Columbia Institute of Technology, who is running and building out a smart grid on campus. And they also have an Internet of Things Center of Excellence that they're building out. And then the University of Waterloo, my old alma mater, and Waterloo is actually got the Institute for Complexity and for Innovation in Complex Systems, and we're currently working with working on putting proposals together with them to do environmental and smart city projects. So on that note, here are some things for everybody on the call. If you are interested, what we are always looking at is partners and that want to join the alliance. If you are an industry, small business, you have a startup idea, you have a new technology field you're trying to do, or you need access to a really large platform that you can't afford, but you have an application you want to build, become an industry partner. join us. If you're an engineering firm and you want to go through and start using this to go through and deliver engineering services, or if you're running a utility, join as a potential project partner. Or if you're an associate and you're a small, or you just want to participate as a core researcher, as an academic partner, you can also be an associate partner. We have roles for everybody on projects. It's an informal alliance that we're formalizing, and we're continuing to go after. And we know where we basically jointly fund with research projects with various government agencies, different projects that we can basically drive, and then we help to go through and commercialize the technology. So what are some of the things that we're focused on today? So some of the applications that we are driving, smart cities is where we grew up. We basically have worked many years with city government looking at how to go through and manage transportation networks, utility grids, water, wastewater systems. What we found is that there's a lot of technology out there, but we have to find a way to make use of it. So we look at things like, is there a way that we can find contaminants in water and wastewater flows without actually putting in all the sensoring technology in the field, and use flow patterns and pump stations and lift stations to find it? That's part of a smart utility or a smart city model. If we look at transportation patterns on a transportation grid, we actually, as an example, are working with the City of London in the UK on running their cycle hire network. We look at availability numbers. We look at usage patterns for their bicycles in different areas, how many people are going to use it at a certain train station when trains arrive. That's part of a smart transportation system. And then what about hospitals? Well, we start looking at things like rooms or emergency rooms, or how do the different transportation flows and the people and the patient flows in a building work to manage and isolate certain wards, and be able to look at the different areas so that we can optimize how to move patients around, how to go through and deliver services in a cost-effective way, and how to make sure that we're managing any sort of virus spread within those environments. So those, again, are different ways of looking at smart hospitals, which then leads into facilities in the overall campus environment, which Jen has done a much better job of describing than I could probably do. And on the last note, I always like to share a little bit as to who we are. So FuseForward, we are the ones that are driving the remote control series. We are accelerating digital transformation, and we work with critical service providers, be that utilities, energy plants, emergency services personnel, healthcare organizations, life sciences, and education campus environments. We build intelligent systems. We run cybersecurity services. We have security operations centers in multiple jurisdictions. We have advanced analytics solutions that we provide and are continuing to deliver both as turnkey solutions and as a subscription-based service on the cloud. And we continue to provide and manage those solutions, providing it with cloud managed services. So final note, if you want to get started with us and some things to share, you've got some ideas, you've got some clients, you've got some organizations that are interested in piloting a project, call us. Reach out to us on our website. We're looking for power generation plants to do digital twins on. With this new green movement as part of the COVID recovery models in Canada, the US, and Europe, there's definitely opportunities for us to basically look at smart grid projects and how we can basically show how new green infrastructure and power demand generation and power supply, power dispatch can all be managed. We're looking at things for single room simulation models. Can we look at things where we can over sensor certain rooms to look at how new sensoring technology works and determine what the safe capacity levels are inside those rooms? Can we look at things like virtual field crew operations? We recently did a remote control series on a virtual operations center for utility organizations. So we still look at that and say, is there a way that we can run, instead of having one or two central facilities to go and do emergency or situational management and operations, that we can use a more distributed environment? That's virtual crew dispatch. We have technicians in the field that do certain things, but they're managed remotely by high-skilled engineers or technicians that have additional certifications that can basically do that using things like augmented reality technologies in the field. So on that note, I do want to leave it open and give us a few minutes here that if anybody has any Q&A for myself or for Jen, let's open it up to some questions in the field.
We've got a lot of questions coming in, guys. Would you like me to read them out to you?
Sure. Why don't you do that? And
Yeah.
maybe what we can do is we can answer these online.
Yeah. Okay. So is there some information available on what virus sensing technologies are available?
Virus sensing. So Jen, maybe that's one for you, but I know of a couple of firms that I know that have got new sensor technologies using lab-based readings and new kinds of biochemical signatures. What about yourself? What do you know about HVAC and other kinds of air sensors or other technologies around that?
To be honest, very, very little. I know COVID has really sparked that. I had actually completely misinterpreted the question differently, and I thought we were talking about,
Computer viruses?
cybersecurity, computer viruses actually attacking the network. And I was thinking it was a perfect question for you.
And I think about the biochemical side of the house.
The problem with viruses, of course, is that they're incredibly tiny. They're microscopic. We can't see them, and we will never be able to visually detect them. But there are certainly technologies that are being actively developed to try and detect them within the COVID. One of the nice things about HVAC systems is that most of them have some sort of disinfection mode or the ability to install it. So you could put UV treatment into HVAC. We have filters, they could be upgraded to HEPA filters that might well require you to upsize the fan motor, but there are different aspects to it. I think there's been a lot of work in terms of the visualization of the water droplets, the actual aerosols, rather than the viruses per se.
Yeah.
I don't know of any real-time sensors that can pick up RNA floating in the air.
Well, and that's the air. On the water wastewater side, we do have, there is a firm that we are in discussions with out of Halifax, Canada, who actually has an in-stream water wastewater sensing technology, and they built a COVID, like a virus detection mechanism using different kind of lab-based, and it's an in-stream lab monitoring technology. Okay. Another company in Canada is a company called FredSense, which is more of a lab-based. I'm not sure about the COVID, but again, they're using more of a biochemical signature model to going and doing that as well. And then there's another firm out of Toronto, which has in-stream water, and they're using spectrometers to do signature analysis. So those are kind of some of the new that's on the water wastewater side as well. Okay. Another question. Carla, I'm going to let you go through and read these ones out.
Great. Okay. How many different types of sensors so far in the system?
Oh, I really, well, in terms of what was on the original building automation system, I would guess probably in the order of 20 to 30 different types, but they're serving 10 to 15 different kinds of services. So you wind up, once you actually go through, we have several hundred different types of sensors, in the sense that you'll have air temperature. So you've got temperature sensors, that's a type. Some of them are air temperature, some of them are water temperature, some of them are within a room, some of them are within equipment, some of them are within a duct, some of them are inside pipes, some of them are actually differential sensors. So, and that's just the heating, ventilation, and air conditioning side. Once you start getting into lighting, so lux sensors, acoustic and noise meters, people counters, which you can use sometimes with Wi-Fi connections when you're basically counting devices rather than people, or also when you're looking at infrared sensors or any sort of kind of imaging sensors, you can actually count the number of literal warm bodies to get a sense of the number of people, so that you can do people counting without violating privacy. You can say that those are all different kinds of sensors. So very easily, I would say we're going to have upwards of 50 different sensor types in the broadest possible category. And as soon as you start specializing and differentiating, it's probably going to be several hundred types of sensors. Hence the heterogeneous data problem.
Exactly. And of course, I think I even shared the other ones on the water wastewater. We haven't even gone into that. Jen's talking about the stuff in the building. On the civil infrastructure side, we're looking at much different ones and other kinds. Not necessarily, we're not sure if it's going to be part of this project, but there are other things going on related to new sensoring technologies out there as well.
Great. Well, next question, and I might mess up the pronunciation here. Are you using ENVIRONMEN or have other good experiences with different wireless connections? Have I messed that up?
Wireless. So let's talk about wireless. I think what one of the things that we're doing with wireless infrastructure right now, Jen, we're doing everything wired, if I am aware, Because
In this particular building, yeah, we're building a new building at Ryerson, which is going to have some Zigbee-enabled wireless devices as well, and some PoE devices, which is power over Ethernet, so we don't even need to run wiring. So
yeah, so that's kind of where we're at. We're looking at this as part of the cybersecurity model right now as well, is keeping as much wired as possible so we don't get interruption. Sensor is a different, and looking at the edge, that's actually a research area that we're looking at right now, is what else we can be looking at to secure wireless. And that's really when we start looking at the edge and the IoT networks. Different research domain, not necessarily the purview of this research specifically, but there are other labs that we've been chatting with that have expertise in that area.
yeah. Now, it's worth noting that some of the a lot of the extra IoT sensors that we're adding to the lab that weren't part of the base legacy system are actually they're actually going to be wireless devices, and we're going to be communicating via Bluetooth or direct cell phone feeds, just simply because sometimes it's easier for us to do that. Things like putting something in over a doorway that otherwise we couldn't wire to. So sometimes wireless does give you good opportunities, but we do need to be aware of the potential data, cybersecurity ingress risk with that. I'm afraid to say I'm not familiar with LoRaWAN, so.
Couple of monitors going here, and I keep looking over at what the next questions are.
Well, I've had my pronunciation corrected. LoRaWAN was what I was supposed to say, so apologies. Next question. Do you use quantum computing to support the smart city projects and other projects?
So I'm going to jump on this one, Jen. So no, we don't yet. Is it an area that we're interested in? Yes. But do we know a lot about it? There's always the research area right now. We actually, FuseForward is currently, we are aware of the Quantum Institute that has just been started up with Simon Fraser University, and what they're trying to lead in the way of leading the charge on quantum computing. So it is an area of interest. Are we using it today? No. Will it help speed up that billion processing problem? Potentially in the future. Problem is it commercially ready? What can we do? Or is it still in the research realm and validation realm for any sort of applications? So we're trying to get things out into the field right now that we can basically commercialize within the next year, not stuff that is going to take a couple of years to commercialize. We do use cloud computing, and where they bring things to the table that they're providing that capacity, we do look at those kind of computing techniques as part of the infrastructure that we can leverage. Jen, any thoughts on your side? You want to go and start becoming a quantum computing expert?
I think between the building optimization and everything else is there's a lot going on.
Yeah. I do see one more question. Are we using a lot of open source solutions? So our premise on this project and all projects is open source as much as possible, so we can also go through and look at the code and understand what's underneath it, so that we can challenge it for basically cybersecurity and other pieces around that. It also creates the community around a lot of this. We look at a lot of the industry alliances. Jen, you might be able to share a little bit more of that, but even from FuseForward's perspective, we basically look at open source. Even when we build proprietary, we look at open standards and how we can leverage and link things in through an open standards model. It's the only way that this will be adopted into the market, in my humble opinion.
Yeah. And a lot of the ontology work that we've been doing has been drawing from some of the open source ontologies. Brick and Haystack were both reviewed in detail to see what was relevant and where we needed to expand upon it. And I actually was speaking to the W3C group, which is the World Wide Web Consortium, looking at actually data structures for this kind of streaming. We spoke to them a couple of months ago about the work that we were doing and how this fit within those larger ontologies. So at least from a data structure perspective, the reality is legacy systems, there is no open source building automation system that is at the scale to serve commercial buildings. You can build something out of Arduinos, you can build something with some of the off-the-shelf parts, and there are some things coming up there. But these have typically been companies who have spent a lot of money over the last 20 years developing their networks and their systems and their control modules. And it's not open source within it, but it's BACnet compatible. So we can speak with BACnet, which is the communication protocol developed by ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. It's a bit of a mouthful, but basically every building in North America will communicate with BACnet or sometimes with Modbus or LawnWorks. And those are kind of the open, LawnWorks isn't open, but BACnet and Modbus are very consistent standards used across the domain, and any device that you're using has to be able to work with those. We are working with things like Zigbee as an open protocol for wireless, but the actual equipment, if you're buying a boiler from a certain manufacturer, their controller is going to be proprietary to that boiler manufacturer. It simply hasn't gotten into the mechanical side of the business yet.
Well, it looks like we've got our questions answered. I'm going to turn it over to Carla for the final on this one. I want to thank everybody first off for listening, and I also want to thank Jen for jumping on to our remote control series all the way from Scotland, even though you're in Toronto virtually in many times. And we're looking forward, as I said, from a FuseForward perspective, to continue to drive this project forward over the next 4 years.
Thanks
Carla,
for having me.
you.
It's been great.
Yeah. Okay, well, thanks for joining us, Jen, and thanks again for the presentation, Mark. And thank you everyone for joining us this morning. This is the last remote control for the year. So it's been great having, getting involved with everyone this year, meeting a lot of people virtually. We will be running this again in 2021, and we'll be advertising the next session in the new year. So if you'd like to stay in touch, if you would like to subscribe, we have the subscription in the chat there. We are also on LinkedIn, we are on Twitter, we are on Meetup, so you can connect with us on any of those platforms. Drop us questions, we'd love to see you there. And I think that that is it for the moment. Okay, there's some questions going on there, but I think they're all being answered. Thanks everyone. Have a great holiday season and a great new year, and we'll see you in 2021.